If you took physics with us in grade 11, you'll know that in grade 12 now, we've been repeating several topics, but modifying how we think about them or expanding them and generalizing them to more situations than they were applicable for in grade 11. So fields is going to work the exact same way. In grade 11, we talked about fields using the formula F equals QE. Electric force equals charge times field strength. And we're going to generalize that for more situations. So in the late 1700s, Charles Coulomb was studying force between charges. And he figured out a whole bunch of different things through experiment. He found out that as he increased the size of the charge on the two charges that he was working with, the force between them also increased. Okay, and in fact, when he doubled the charges, the electric force doubled. When he doubled the total charge, the electric force doubled. So that told him that the force between two charges depends on the size of the charge, which makes sense. The other things that he found were as he changed the distance between them, the force also changed. So if he would double the distance between the charges, the amount of force would be cut in quarters. Okay, so that told him that the force between two charges depends on the distance between them, but specifically the square of the distance between them. And so from there, we come up with Coulomb's law, which looks like this. Fe equals KQ1 Q2 over R squared. Okay, and Q1 and Q2, those are the charges that are interacting with one another. Charges, and those should be measured in coulombs, but there is a situation where you can measure them in ECs. This K value here, this is Coulomb's constant. We're just going to write constant. And this R value is the distance between them, center to center. Now we're going to work with point charges, which means that we're assuming they have no appreciable size. And so we don't have to take into account the distance from the edge of the charge to the center of the charge, since they have no size. Okay, so the R is the distance between charges. And that should be measured in meters. Okay. Now, the one thing that I haven't filled in here is what this constant actually is. So Coulomb's constant turns out to be 9 times 10 to the 9. 9 times 10 to the power of 9. Okay? And usually when you have a direct variation like this in a formula, you are going to find that there's some sort of constant that relates the two numbers to each other, and it turns out this one is 9 times 10 to the 9. Now we need to remember how charge is measured. You can measure it either in elementary charges, ECs, or in coulombs. Now one elementary charge is the charge on a single proton or single electron, hopefully you remember that, and a coulomb is 6.25 times 10 to the 18 electrons, or protons. Okay, and so we can convert between the two. You see the conversions up here. 1 EC is 1.6 times 10 to the negative 19 coulombs, and 1 coulomb is 6.25 times 10 to the 18 ECs. Okay, so we're going to use that in this example right here. One model of the hydrogen atom assumes a stationary proton is orbited by one electron with a radius of 3.0 times 10 to the power of negative 10 meters. Okay, so this is not saying that the electron has that radius, but the radius of orbit is that. What is the electric force between the electron and the proton? So, electric force equals KQ1, Q2 over R squared. This is a vector. But these charges are not vectors. They're positive or negative, they have polarity, but they are not vectors. So we're going to figure out the direction of this force based on what's happening in the situation, based on what the polarity of the charges is, but we'll talk about that in a second. So electric force, in this case, is 9 times 10 to the 9 times Q1, which is 1 EC, right? But 1 EC is 1.6 times 10 to the negative 19 coulombs. Okay, so that would be the proton. And then the electron is the same but negative. Divided by R squared. So R is 3 times 10 to the negative 10 meters, and that's squared. Okay, now you're maybe going to notice that I didn't put the negative in for the electron's polarity, right? The only reason that that would be needed is to figure out the direction of the force, right? The negatives and positives in the polarity of the charges, they don't make a difference to the magnitude of anything. They only make a difference as far as the direction goes. So let's think about how this would work. We know that like charges repel each other and unlike charges attract each other, okay? And so you can figure out the direction of the force without putting in the polarities of the charges at all. I know that this is an electron and a proton. They have opposite charges, and so my direction on my force is going to be attractive. Okay, but if they were the same type of charge, if they were both positive or both negative, it would be a repelling force. So I don't need to put the polarity in the calculation itself in order to figure out the direction. But if you would, if I would make this positive 1.6 times 10 to the negative 19 and make this negative, you would end up with a negative force, right? And in that case, that wouldn't be telling you the direction of the force. It wouldn't be backwards, how we normally think about negatives. It would be telling you that it's an attractive force. So if you want to put the polarities in, you have to then remember that negative means attractive and positive means repulsive. Okay? But I find that that's not easier than just figuring out the force direction logically. Okay? So when you figure this out, the electric force is equal to 2.6 times 10 to the negative 9 newtons. And so this is attractive. You can say that a number of ways. So the forces toward each other or what have you. I'm going to say attractive. It's an attractive force, not a repulsive force. Here's our more complicated example. 4 identical charged spheres, each with a magnitude of 5 microcoulombs, or 5 times 10 to the, 10 to the negative 6 coulombs, micro is times 10 to the negative 6, are arranged as shown below. I've drawn you that picture. Calculate the net force, net electric force on charge A. Okay, so let me just show you which is which. This is charge A. All the rest of them, it doesn't really matter what you name them, but let's just go B, C, and D. Okay, now in order to figure out the total electric force on A, we need to figure out what's the force on A because of B, what's the force on A because of C, and what's the force on A because of D, and then add them up. Okay, so there's a bunch of steps to this thing, but the nice part is that all of the distances are the same and all of the charges are the same. So we really don't have to redo the calculations over and over again. There is one thing that is not the same though, and that is the distance from C to A. This distance is not 25 centimeters like the rest of them. That distance is the hypotenuse of a right-angled triangle with sides of 25 centimeters. So first of all, we'll need to figure out what that distance is there. We'll call that distance D. Okay, and so D, using a squared plus b squared equals c squared, D is going to be the square root of 0.25 meters squared plus 0.25 meters squared, or just 2 times 0.25 meters squared. Okay, and that ends up equaling 0.35355 meters. Now, in the end, you'd rather probably not use a rounded number, even though I've kept 5 decimal places here. It's just as good to use this number, the root there, as the R value when we need to calculate that part of the force. So what we're going to do is calculate the force on A because of B, the force on A because of D, and then we'll do part C. Okay, so the force on A because of B is equal to KQA QB over R squared. Okay, putting in the numbers, you get 9 times 10 to the 9 times 5 times 10 to the negative 6 coulombs times the same thing, 5 times 10 to the negative 6. So let's just make that squared for the sake of space. And the distance between them is 0.25 meters. That needs to be squared as well. And so we find in the end that the force on A because of charge B is 3.6 newtons. Okay, and looking at them, judging by the fact that they're opposite charges, they're going to attract one another. But since we're looking at A specifically, A is going to be pulled toward B. So that would be toward the east. Okay, now figuring out the force on A because of D is quicker because we're using all the same numbers. It's the same distance, they're the same charges, so all of it is the same. Let's not redo that. It's 3.6 newtons. It's just that the direction is going to be different. In this case, A is attracted to D, which means it's being pulled south. So our second force that A is experiencing is 3.6 newtons toward the south. Now the final thing that we're going to do is the force on A because of C. The force on A because of C is KQAQC over R squared. But we're not going to write that all down. We're going to put the numbers in right away. 9 times 10 to the 9 times 5 times 10 to the negative 6 coulombs times 5 times 10 to the negative 6 coulombs, because they're both the same charge, divided by R squared. Now in this case, I'm going to take this unrounded version of the distance and put that in here. So I'm doing the square root of 2 times 25, not 25, 0.25 meters squared. I'm doing the square root of that, and then I'm squaring it. So really I'm just, you can get rid of the square root there. Okay, and so what I end up with once I have done all of that is that the force on A because of C is 1.8 newtons. Okay, that force is going to be at an angle of 45 degrees, right? Because all of the sides are the same, I know that this is 90 degrees in here, And I know that each of these is 45 degrees then, because all the sides are the same. So this is going to be repelling each other, right? So A is going to be pushed away from C, and so the force it's going to experience is, let's say, north 45 degrees west. Okay, so now we're supposed to add up these three forces: 3.6 east, 3.6 south, and then 1.8 north 45 degrees west. Now we can just put the force from B and D together in a triangle, but the force from C is at an angle itself, and so we should split that one into its components so that we can more easily add it together. Okay, and when I do that, north component and a west component, like that. This was my 1.8. Okay, and I know that this is 45 degrees. And so I know that the west component and the north component are going to be the same, right? So all I need to do is 1.8 times the sine of 45 degrees, and that will give me both components actually. Okay, and it turns out that when you do that, you get 1.273. 1.273. Okay, now we need to put together our x components and our y components. So here are my x components. So I have 3.6 east and 1.273 west. So 3.6 minus 1.273. That equals 2.327 newtons toward the east. And then when we do the y components, we're doing exactly the same thing. 3.6 minus 1.273 gives us 2.327 newtons toward the south. Okay, so now we have one x component, one y component. We need to put them together to get our total force acting on A. And here's what it looks like. We have an east force acting on A and a south force acting on A. They're exactly the same, 2.327 and 2.327. And so our total force looks like this. This is the total electric force on A. Since both of those components, the x and y components, are the same, we already know that this is going to be 45 degrees, but you could confirm that using trigonometry. So we're going to do a squared plus b squared equals c squared to figure out FA. So the force on A, total force, is equal to the square root of 2.327 squared plus 2.327 squared. So 2 times 2.327 squared so the total force on A, finally, is 3.3 newtons. East, 45 degrees south, or south 45 degrees east.